Hello, good morning everyone. I am Ravi Kumar, Associate Professor in the Department of Mechanical Engineering, ATME CE Mysuru. Today I will be conducting an experiment or giving a demo on an experiment to find out the overall heat transfer coefficient of a composite wall. And this experiment is a part of a lab component of a heat transfer subject for 6th semester mechanical engineering students. So let us go. The objective of this experiment is to find the overall heat transfer coefficient of a composite wall. So let us find out first, let us know what is composite wall first. A composite wall is the composition of two or more materials of different thermal conductivities arranged in series or parallel. In this case, we have got it in parallel mode. And this composite wall is a setup where three different materials of different thermal conductivities put together to form one part. The applications you can see in the wall of a refrigerator, there will be outside a metal sheet will be there, and inside another fiber sheet will be there. In between that, thermocols or any other heat resistant materials they will be putting it. And the hot cases, the thermal flask body, and even your water tank, it will be having a different layers at the outside, mid and inside also different layer, different material will be there. And the wall of your room where you are sitting is also a composite wall because it contains the cement layer and the brick part of it and the paint part of it. All are different materials having different thermal conductivities. So in the heat transfer problems, sometimes we need to find out the overall heat transfer coefficient. Each different have got different thermal conductivity, and when you want to find out the rate of heat transfer through this thermal, what do you call, composite wall, then we need to find out the overall heat transfer coefficient of this composite wall. So today, this experiment is going to help us to understand the procedure and the principle behind this composite wall. Okay, let us go. Let us see the setup, experimental setup what we have got here. As you can see, these are all, this is the setup we have got in our lab, and three different materials I have taken is mild steel, wood and copper, and mild steel is put at the bottom, and above that we have got the wood, and above that we have got the copper. And if you can see, this is the setup here in the panel here on the setup. The bottom we have got mild steel, the mid we have got the wood, above that we have got the copper plate, and all are of the same diameter, a circular plates of some thickness, right? And at the bottom you have got a heating element here. The composite wall is heated from the bottom using electrical heater, and the heat passes through all the three layers and reaches the top. And at the top I have got a cooling chamber wherein I am going to cool the top surface of the composite wall by passing through a cooling water. Sorry. And this setup is put on a table here, and this is the panel where I've got all the controls and the readings where you can take the readings of different values, different parameters. So I'll tell you when I go to this conduction of experiment about all the controls. This is the power control, this is the heater control, this is the place where you read all the temperatures. It's a digital meter, digital display. It will give us the temperature at different points in the composite wall, and this is the place where you take the voltage, and this is the place where you take the current reading, and this is the place where you control the flow of cooling water. At the top, as I said, the rate of flow of cooling water is controlled using this knob here, and of course the rate of heating of this at the bottom is controlled with this dimmer stat at this point. Okay, this is the whole setup, and I've connected everything. The cooling water is also connected, and the power cable is also put into the wall socket. And the setup is like this, and as I said, three different materials are taken: mild steel, wood, and copper. All are with different same thickness. L1 is the thickness of mild steel, L2 is the thickness of wood, and L3 is the thickness of copper. You can also take different thickness also, it doesn't matter, but only in this case we have taken the same thickness. It doesn't matter because L1, L2, L3 values may be different also. and all these three things. And the temperature, the thermocouples are placed at critical points where we need to measure the temperature. One is here, T2 is the bottom surface temperature of the mild steel. T3 is the junction between the wood and mild steel junction temperature, and T4 is the junction temperature between copper and wood, and T5 is the top top of the copper surface temperature. So like that we have got, and the diameter of this whole, these are all circular discs, and the diameter of that is 150 mm we have taken. So these are the specifications of our experimental setup. Right now, let us go with this is the specifications here. Mild steel 10 mm thick of 150 mm diameter, wood the same thickness and same diameter, copper is also the same thickness and same diameter. Heater, we are using a 400 watts heater to heat up the composite wall. And the temperature points we have taken as T1 as heater temperature, T2 as the temperature of mild steel plate at the top surface, T3 temperature of wood at the top surface, T4 temperature of copper plate at the top surface, and T5 this top surface is the junctions, and T5 water inlet temperature, T6 water outlet temperature. So these are the reading we are going to note down while conducting the experiment, and this is going to help us to calculate result. The procedure, let us understand. First of all, we have to switch on the mains and the console. The power has to be taken to the panel, and you have to set the water flow rate. It will be usually 0.2 to 0.3 liters per minute we will put, and this flow rate is varied as per the heating rate. If the heating rate is more and the cooling rate also should be more, then you have to go for higher flow rates. And then the heat input to the heater is fixed again using the dimmer-stat. The heating rate and the cooling rate has to match, right? I'll tell you how to do that. And after steady state is reached, we all know what is steady state is. Steady state is the condition where the heat coming into the rate of heat flowing into the composite wall is equal to rate of heat flowing out of the composite wall. So that the temperatures at different points in the composite wall becomes constant. All these things we have discussed it in our theory classes. We all know what is steady state, and the system takes some time for the steady state to reach. Till then we will be adjusting with the dimmer-stat and the water flow rate, so that the rate of heating at one point matches the rate of cooling. Then the steady state is achieved. At that state we are going to note down the readings, because all these values we are going to calculate is a steady state conditions values. Okay, that's what the procedure. And then by varying the heat input to the system through dimmer-stat, and the readings can be obtained, right? So that's the procedure, simple experiment. And this is the table column where we are going to record all the readings. You can see voltage in the first column, current in the second column, and water flow rate. That is LPM. Actually our meter gives it in LPM. We need to convert that into kg per second. Both LPM and kg per second are the flow rates. We know that. In the formula we need it in kg per second. And the temperatures at different points, T1, T2, T3, T4, and T5, T6 are the water inlet and water outlet temperatures. So these readings need to be taken at after the composite wall has reached steady state conditions, right? Right. Now the calculations, once we note down all the values, what are the calculations, how to find out that? We know the heat flow through the composite wall is nothing but the heat supplied to it. And we are going to supply the heat through a heating coil, electrically heated, and the heat supplied is given by Q is equal to V into I, voltage into current. Both we are going to note down in the panel how much heat we are going to supply, and these values need to be taken down. As I said, I am repeating it, only after the steady state condition is reached. And this is Q, that is the rate of heat supplied to that, and that is the same amount of heat, as we know it's all steady state conditions, is going to flow through the first component of the composite wall. The same heat is going to be flowing through the second component, that is the wood, and the third component is the copper, and through that all the same amount of heat is going, because it has reached the steady state. This formula we all are familiar. This is the Fourier equation of heat conduction, and from that we got this. Q, the heat supplied, is equal to V into I. We know that the same amount of Q is also flowing through all the three slabs. Okay, and these formulas are from Fourier equation. We know that, we studied that in the theory classes. And where of course K1, L1 and K2, L2, K3, L3 are the thermal conductivities and the thicknesses of different materials. We all know that. And we need to find out the K1, that is the thermal conductivity of the first material, the mild steel. From this formula, you can see here Q is equal to K1 A1 T1 minus T2 by L1. From that formula, we can write K1 is equal to Q into L1 divided by A1 into T1 minus T2. So this T1 minus T2 is the surface temperatures of the steel plate. First one, the K1, the steel plate. Similarly, you can say K2 is equal to the same formula only for different T2 and T3 values. Right? Temperatures of the surfaces of the bottom surface and the top surface of the wooden plate. Similarly for copper plate K3. So once we find out K1, K2, K3 using this Fourier equation, we are going to find out the overall heat transfer coefficient, which is given by U naught, which is equal to 1 divided by L1 by K1 plus L2 by K2 plus L3 by K3. This formula again, we know how we got it in our theory classes, where we have derived this, right? From the basic equations we have derived this. The same formula I am going to use, where L1 is the thickness of the first material, which is a mild steel, and K1 is the thermal conductivity of the first material, which is mild steel. L2 is the thickness of the wooden material, the second material, and K2 is the thermal conductivity of the wooden material, wooden plate. Similarly, L3 and K3 are of the copper plates. And if you use this formula, you can directly get the U naught, that is overall heat transfer coefficient in watts per meter square Kelvin. It is such a simple experiment where you need to only start heating the element and at the same time cool at the top. Let the system reach steady state conditions. Note down the temperature readings, water flow rate readings, and the voltage and current readings, with the help of which you can find out Q as well as K1, K2 and K3 and put them together here in this equation to find out the overall heat transfer coefficient. Okay, now let us go to the setup where in a small video I am going to give the comment here and I will show you how to conduct the experiment now. Okay, right. Look, this is the setup we have got here, and this is the panel and the composite wall. That's the panel there, and this is the composite wall that I was talking about, which has got the three different materials put one above the other, and from wood, mild steel, wood, and copper, all the three put together. From the bottom, we are going to heat it using electric heater, and the top we are going to cool it using the flow of cooling water. Heating from the bottom and cooling from the top. This rate of cooling at the top is controlled by the flow of rate of water, as I said, and that is controlled using this knob here, which I can adjust the flow rate of water as per the requirement, and the rate of heating from the bottom can also be controlled using this thermostat, which is going to be turned left or right depending on our requirement to increase the rate of heating or decrease the rate of heating. This panel is going to give us all the readings required. Voltage and current are read through there, and this is the place where we need temperatures. These are the switches to supply current, and now I am going to switch on the power. Now the power switch is on, the power has come to the panel. Now the second is the heater switch. I am going to switch on the heater switch, and now the coil is heating the setup. Coil is heating the composite part from the bottom, and the heat flows from the bottom to the top, and at the top it is cooled. The flow rate, current or flow rate of water both need to be balanced, so that the rate of heating from the bottom is equal to the rate of cooling at the top, so that the steady state, right, from the bottom it is heated, top it is cooled, the steady state is achieved. At that point we are going to note down the temperatures at this part, where the channels are selected for different temperatures, different junctions. Thermocouples are connected to different channels, and as I press the button there, I can note down the different reading temperatures. At the same time, note the voltage, current, as well as the flow rate of water and the thermostat, and all those things are tabulated, and the calculation is done. Okay, this is what the experiment is all about.